Neanderthals, our closest relatives. Scientists have been trying to solve their mystery for decades. Why did they become extinct? And could there be something of the Neanderthal in us? The Max Planck Institute for Evolutionary Anthropology in Leipzig, Germany. For the first time ever, researchers have presented the gene sequence of an extinct prehistoric human. The geneticist Svante Pääbo, one of the directors of the institute, has been working on decoding the Neanderthal genome since 1997. Finally, he and his team have achieved their goal, and their findings have caused a worldwide sensation. The Neanderthal has actually left traces in the genome of modern humans, of between 2 and 4%.
The fascinating thing is that we're a mosaic. Our genome is a kind of mosaic. When I go across a chromosome, I'm in one part more closely related to you than to another person. Then, as we go further, I'm perhaps more closely related to some other person than to you. And then, more related to someone in Africa than to you, and now and again, more closely related to a Neanderthal than to you. So what these results actually show is that this large mosaic, this great big puzzle, contains parts which are from the Neanderthal.
The greatest difficulty for the scientists: avoiding contamination of the fossil specimen with their own DNA, and with the DNA of bacteria present on the bones. A special clean room was set up in Leipzig. Only here could specimens be taken. The researchers developed numerous new techniques to separate ancient DNA from new. Vindija near Zagreb in Croatia. Most of the bones for the Neanderthal Genome Project were found here. The limestone cave provided ideal conditions for their preservation. It too played a role in decoding the genome. The icon in German archaeology, discovered near Mettmann in 1856. The Neanderthal was named after this fossil. To throw light on the Neanderthal's relationship to modern man, the researchers sequenced 5 additional genomes. They stem from people from all over the world. The comparison with the Neanderthal genome brought completely unexpected results. It is obvious that Neanderthals and early modern humans mixed. However, the inheritance from the Neanderthal is unevenly distributed across the world.
The most astonishing thing was that we find this small contribution in Europeans and in Asians, but not in Africans. It seems to be something that Europeans and Asians have in common, but which is missing in Africans. A small part of the Neanderthal genome.
Why are the genes scattered so unevenly across the world? Svante Pääbo and his team can only speculate.
The great mystery. How can it be that the Neanderthal has contributed to individuals in parts of the world which were never actually inhabited by Neanderthals? The most likely hypothesis we have is that this mixing with Neanderthals happened very early, with ancestors of the ones we're examining from Croatia. The most likely area for this is the Middle East.
100,000 to 50,000 years before our time. Anatomical modern humans migrate from Africa and encounter Neanderthals in the Middle East. The groups mix. This takes place before Homo sapiens' triumphal march across the world. In their genetic pack, they carry with them a few Neanderthal genes. It is the researchers' goal not only to get to know the Neanderthal better. They find information in the genes of our extinct cousin which concerns all of us. By discovering what we have in common and what makes us different, we are discovering our own history.
If we want to pinpoint what is unique in terms of genetics about the human being today, then we can compare ourselves not just with chimpanzees, with whom we share a common ancestor of between 5 to 7 million years ago, We can also compare ourselves with the relative who's closest to all of us, the Neanderthal, with whom we share a common ancestor of 300 to 400,000 years ago. We can say which mutation in the genome is unique. This is the first really important objective.
The team is also familiar with the genome of great apes, such as chimpanzees, so they are in the best position to compare. They can determine exactly which gene variations are unique to humans. This answers questions about why we were so successful in the history of evolution. And indeed, the researchers already have a couple of candidates in mind.
We can then compile a catalogue where we have the strongest evidence of positive selection. What I find extremely interesting is that there are several areas related to mental development, for example, mutations which lead to autism or schizophrenia in people today. This suggests that genes which have something to do with this kind of mental ability mutated. Of course, this doesn't mean that Neanderthals had this problem which led to this mutation. But it does show that these genes in this area somehow changed.
These candidate genes can be examined specifically for this, for example, on a mouse model developed at the Max Planck Institute. In Leipzig, Wolfgang Ehnert is examining the FOXP2 gene. In humans, it's connected to the ability to speak. Mice have a variant of this gene and can only squeak. But what happens when the mouse variant is replaced by the FOXP2 gene? It causes significant changes in one area of the brain.
We are one step further and say, okay, this change somehow affects the mouse's brain, and it does something to the mouse's brain in such a way that we think that we can relate it to certain language-relevant characteristics. And we examine it further in order to define it more exactly, but we have taken the first step. It does something to the nerve cells and to areas of the brain which are responsible for human language.
The development of language makes human beings special. Using the mouse model, the Max Planck researchers want to find out what role the FOXP2 played in this development. If the mutations in the gene prove to be decisive, it will mean that this also benefited our cousins because they had the same version.